Okay, can somebody remind me where we stopped? Let's go all the way back up here. Okay, if I remember correctly,
I know we did the thing about the orbitals
uh-huh.
and a lot of the,
Did I discuss this?
yes.
And did I go through this?
Yes.
Okay. Okay, so did I talk about valence electrons and core electrons? No?
Yeah.
All right, so let me comment from there. All right, so very important for you to be able to distinguish between what are known as the valence electrons and the core electron, right? Now, the valence electrons, they belong to what is called a valence shell. And the valence shell is that shell that is the highest energy shell that is occupied by electrons. All right? So the electrons that are located in the valence shell, we call them valence electrons. All right? And what you'll find is that for the main group elements, there's a relationship between where the elements are and their valence shell, right? And basically, what you'll find is that the number of valence electrons that is present is equal to the group number of the elements in the main group region of the periodic table, right? So elements in group 1A will have 1 electron on its valence shell. Elements in group 2A will have 2 electrons, and so on, all the way over to 8, all right? So that is true for the main group elements. Now, when it comes to the transition elements, things are a bit more confusing. So we don't see that exact correlation between the group number of the elements in the transition region of the periodic table and the group numbers, all right? Now, the period number would be the same as the principal quantum number of the valence shell, all right? So if you take, for example, the first period, then basically you know that the atoms in that period will have electrons in the first shell, right? And then for period 2, right, the valence shell would be the second shell, and so on and so forth, all right? So that's the valence electrons. Now the other group of electrons are known as the core electrons, right? So basically, there are 2 categories of electrons when it comes to the electron distribution in the atom. You have the valence electrons, and then the other electrons are the core electrons, right? So just to give an example to distinguish between these two, here we have the electron coefficient, the electron configuration of this element arsenic. So this is, of course, the abbreviated version, right? So basically, the valence electrons are those located in the highest energy shell, which in this case would be the 4th shell, right? So basically, the number of valence electrons here represented is 2 plus 3, that's 5, all right? Even though you have a 3d10 here, this would not be among the valence electrons because these 10 electrons would be in the 3rd shell, right? So basically, you have a total of 5 valence electrons, and then as far as the core electrons are concerned, basically it would be 10 from the 3D orbital or 3D sublevel, and the 18 from the argon, and that gives a total of 10 plus 18, 28 core electrons, right? So basically, in the case of arsenic, you have a total of 33 electrons, 28 of which would be the core electrons, and the rest, the 5, would be the valence electrons, right? So it's very important that you know the difference between the two because of what we're going to talk about next. What we're going to talk about next is how do we determine the electron configuration of ions, right? So we know by now how to determine the electron configuration of atoms. Now, of course, you should go back and recall that in the case of ions formed from atoms, there are 2 ways they can be formed, right? You can either remove electrons from the atoms or you can add electrons to the atom, right? So just to remind you that if you're adding electrons to the atom, then the resulting atom will have a negative charge, all right? Now the question is, okay, if you're going to add electrons to an atom, which is already neutral, then where will those electrons end up, all right? And the answer is very simple. especially for the main group elements, we simply add the electrons to the valence shell of the non-metal atom. All right? So basically, do I have an example here? Okay, so basically, for example, in the case of the oxygen atom, all you have to do is add 2 electrons to the valence shells of the oxygen atom to get the corresponding anion, which would be the oxide ion. And the result of that, as stated here, is that the ion itself will have the noble gas configuration of the element that is closest to it. So in the case of the oxide ion, the electron configuration of oxide will be the same as the electron configuration of neon. All right. So that's basically what happens when you add electrons to a non-metallic atom. Basically, they gain enough electrons so that they end up with the electron configuration of the closest group A element. Here's another example. Bromine, right? If you add 1 electron, now bromine, if you were to look at the electron configuration, has 7 electrons on its outer shell. So basically, you're going to add 1 more electron to the bromine to end up with 8 electrons on the outer shell. And the result of that is that the bromide ion that is formed will have the same electron configuration as the nearest group 8 element, which in the case of bromine would be krypton. All right? And that's basically how we determine the electron configuration of anions. Now, when it comes to cations, things are a bit different because basically, of course, the formation of monatomic cations is resulted from the removal of an electron, right? To form your, or more than 1 electron, to form your positively charged ion, which is a cation, right? So basically, in order to get the electron configuration of the metal ion, we have to start from the configuration of the atom. And this begs the question, which electrons will be removed first? All right. And basically, this is it right here. The first electrons lost are those of the highest principal quantum number or the highest n value, right? Now, if there are other electrons to be removed within the same subshell where you have different L values, then you remove the electrons from the subshell with the higher L values. All right. So for example, if you have electrons in S and P subshells in the same shell, then in terms of removing electrons, you start removing electrons from the P subshell first before you remove electrons from the S subshell. All right. So just some examples here. The first 2 are examples of the formation of anions. In the case of fluorine, this is the electron configuration. And fluorine will gain 1 electron, which will be added to the 2p sublevel, which has 5 electrons. So this sublevel can accommodate 1 more. And you're going to end up with this electronic configuration of the fluoride ion, where this here is 2p6, right? And that turns out to have the same electronic configuration as neon, which is the nearest group 8 element to fluorine. Here's another example. This is the abbreviated electron configuration of sulfur. And in this case here, the sulfur can gain 2 electrons because the 3p4 sublevel has 4 electrons, so it can take on 2 more. And you're going to end up with this. Excuse me. And as a result, this electron configuration would be the same as that of argon. All right. So that's basically what happens when you form anions from atoms. Now, for the ones below, especially for the transition elements, you have to be careful. Let's start off by looking at strontium. This is the electronic configuration of strontium. To form the strontium 2+ ion, you need to remove 2 electrons. Those 2 electrons will be removed from the highest shell, the valence shell, which would be the 5th shell, which has 2 electrons here. So basically, once you remove those 2 electrons, then that shell disappears and you end up with the electron configuration of strontium 2+ to be the same as krypton. Now, in the case of titanium, this is the abbreviated configuration for titanium, right? Question is, where will the electrons be taken from first in order to form the Ti4+ ion? So the way you go about it is you start removing electrons from the shell, which is the valence shell, which would be the 4th shell right here. So you remove these 2 first, and then you remove these 2 next, and therefore you're going to end up with this as your electron configuration for titanium 4+, which is the same as that for argon. And then the final one, you really have to be careful about this, because in this case here, you're going from iron to iron 2 plus. In other words, you need to remove 2 electrons. Where will those 2 electrons be removed from? They'll be removed from the valence shell, which will be the 4th shell. These 2 electrons in the 4s sublevel will be removed, and therefore what is left would be the electron configuration of argon and then 3d6, which is what we have here. All right. Now, so basically, when you get to the transition region, you have to be careful. You have to keep in mind that the first electrons to be removed to form a cation are those from the shell, which has the highest energy. In other words, the valence shell. All right. Now, I think there's another question. Oh, okay. So this question is asking, what would be the configuration of Fe3 plus? Well, that's kind of easy since we know what Fe2 plus is. This is Fe2 plus. So to go from this to Fe3 plus, we need to remove 1 electron here. So therefore, the electron configuration of Fe2 plus, I'm sorry, Fe3 plus will be the electron configuration of argon and then 3d5. All right. Now another question is being asked here, and that is, what is the electron configuration of Sn2 plus? Now, in order for us to do that, we have to determine what the electron configuration of Sn is. So Sn is 10, and 10 has the atomic number of 50. All right. So let me see if I can do this down here. So 10 is 50. So first off, we start off with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So that's 30. And I'm going to need your help. Can somebody refer to that chart? Remember that chart? Where you're given the order of the subshells. I need somebody to refer to that to tell me what comes out of 3d10. I think it is 4p6, but I need a confirmation on that. So can somebody quickly look at that and let me know?
It is. It is.
4p6, right? Okay, so far I have 36. So what's the next subshell after 4p6? What comes after 4p? Anybody? Anybody over there in Zoom? What comes after 4p? S. You sure? Hold on. Oh, okay, 5s. Yeah, that's the number, right? So 5s will have 2. So far we have 38. So what comes after 5s? 4. For D?
Yeah.
Okay, so 38 4D, that gives you 10 right here. And then what comes after 4D? I think it's 5P, right?
5p.
Yeah, okay. So
5P.
5P, and that would have, okay, so just to make sure the electron count is up to date, we have 10, 10, 10, so that's 36, 38, 48, so 50 would be 2 electrons in the 5p sublevel. Okay, so here's my question to you. To get Sn4 plus, I'm sorry, Sn2 plus, what electrons will you start removing first in order to get the electronic configuration of Sn2 plus? Remember, as we said here, the valence electrons are lost first, right? So in the case of tin, which electrons will be lost first? Let me ask. Oh, sorry. Go ahead.
the 5p.
The 5 here, the 2 electrons in the 5p would go first. So that means that the 5p subshell will disappear, and what is left will be the electron configuration of Sn2 plus, right? Now let me ask you another question, which is not asked here. Suppose you're asked to write down the electron configuration of Sn4 plus. Where will the next 2 electrons be lost from?
Would it be the 5s2 or no?
Exactly. The fact these 2 electrons will go, so therefore basically what is left would be the electronic configuration of Sn4 plus, right? So that's basically how you determine the electron configuration of cations. So you have to be careful, you have to ensure that the first electrons to be lost are from the highest shell, and then you just continue going down. And also within the same shell, if you have 2 subshells, the higher energy subshell is the one that will lose electrons first. So therefore, if you have, let's say, s, p, and d orbitals in a particular shell, you start removing electrons from the d subshell, then the p subshell, then the s subshell, and that's basically how you go about doing that. All right. So here is a question. It says, write the electron configuration of CO3 plus in the noble gas core abbreviated SPDF notation. So cobalt has an atomic number of 27, right? CO 27, right? So what I'm going to do is write down the electron configuration, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d 27. So that's 3d7, all right? So that would be the electronic configuration of cobalt. So to get cobalt 3 plus, which is what the question is asking for, where will you start removing electrons? Which electrons will be removed first?
4s2.
So these electrons will be removed first, so that means the 4s sublevel will be going, but you need to remove one more. Where would that one more be removed from?
One of the p's.
Exactly. So here, you're going to end up with 6 here. So the answer would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. And that would be the electron configuration of cobalt 3 plus. Okay, very good. All right, so let's see what's next. Before we do that, let's go to the assignment. I think we can do some more questions from the assignment. Let me see. Okay, so let's scroll down. So I'm sure we did part A already. Okay, so part B. All right. So this question is asking for you to write the complete electron configuration for each of the following ions and determine which one possess the noble gas configuration. In other words, if they obey the octet or duet rule by having a complete outer shell. All right. So let's start off with the first one, the chloride ion. So let me hear what you have to say about that. What's the first thing you would do?
Start writing the electron configuration.
Okay, so in the case of chlorine, let's start out with chlorine first. What's the atomic number of chlorine? The atomic number of chlorine is 17, right? So it's 1s2, 2s2, 2p6, 3s2, and 3p5. All right? So that's the electronic configuration of the chlorine atom. Now, notice you have a negative charge here. So what does that mean? How will you get from the chlorine atom to the chloride ion?
Add one.
And where would you add it to?
The P.
Exactly, so therefore, by adding one electron here, that increases to 6. And that will be the electronic configuration of the chloride. Now, the question is asking also for you to tell whether or not this obeys the octet rule. In other words, basically, is this of a configuration that is the same as a noble gas? And the answer is, well, look at the nearest noble gas, the chlorine. And the nearest noble gas to chlorine is what? What's the nearest noble gas or the nearest group 8 element to chlorine? No, that's not, that's argon, not arsenic. Right, arsenic is AS, argon is AR, all right? Okay, and basically, the electronic configuration of argon is going to be the same because they have the same number of electrons, right? So basically, the answer here is, let me see how the question is worded. The question says, determine which one has the noble gas configuration. Okay, so basically, in the case of the first one, you're going to say, that this has a noble gas configuration, and that's it. All right. Okay. I'm going to skip B because we just did B a while ago in the previous example. And if you understood B, then C should be a breeze, right? So let's move now to chromium, right? So the atomic number of chromium is 24. All right. So for the chromium atom, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then okay, let me see here. So that's 23d4. However, if you remember, this is one of the exceptions I made mention of. Actually, this should be 1 here, and this should be 5. So this is 4s1, 3d5. All right. So that would be the electronic configuration of chromium. So to get chromium 3+, we have to remove 3 electrons. So where would you start removing electrons? Make this full screen. Where would you start removing electrons? Which orbital would you start removing electrons? I'm sorry? Nope. Remember, you start removing electrons from the highest shell, from the valence shell.
4s1.
Right, exactly. Start removing electrons from here. So the 4s sublevel will disappear. And then you're going to remove 2 more from this, and you're going to end up with 3 here. So the actual configuration of chromium 3+ would be 1s2, 2s2, 2p6, 3s2, and then 3d3. And that's it. All right. Okay, any questions about this one? Any questions? Questions? You look puzzled.
What about the 3p6?
Oh, right, thank you. Thank you so much. I skipped over 3p6, which should be here. And then 3d 3. Okay. Any questions? Any other questions about this? Any questions? All right. Is there any more in this section? Oh, 1 more. 2 more, actually. All right, let me clear this here. All right, titanium 3+. So the atomic number of titanium is 22. All right. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d2. All right. So that's titanium. So for titanium 3+, we need to remove 3 electrons, right? So where would you start removing them from?
Four S two,
Okay? And then,
3D.
right, so you're gonna end up with one here. So the final answer would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d1. And that would be, this would be the answer right here. All right? Okay, any questions about this one? Any questions? Oh, by the way, hold on. Did the question say the full configuration or abbreviated? Oh, full, okay. So we're on the right track, all right. Okay, lithium is the next one. And the atomic number of lithium is 3, right? So this one is relatively easy because it's basically 1s2, 2s1, right? That's the atom, right? So to get lithium plus, all we need to do is remove one electron, and this will be the electron removed. So therefore, in the case of lithium, the electron configuration is 1s2, right? So this will be the answer. And in the case of the lithium ion, this will have the same electronic configuration as helium. So therefore, this also has a noble gas configuration. All right, and that's that. All right. Okay, so let me clear this here and scroll down to see if there's anything else we can do. Okay, we can't do that yet. So let's go back to the PowerPoint. All right, so let's talk about magnetic properties, right? Turns out that certain metals especially display different magnetic properties, and these are the type of properties that's associated with magnetism. You have what is known as diamagnetism, which is the weak repulsion associated with paired electrons. So basically, pretty much anything that has paired electrons will display diamagnetism. Now, paramagnetism is kind of more interesting because this is the attraction that a magnetic field will have for atoms or molecules that have unpaired electrons. So any structure that has unpaired electrons will display paramagnetism. And then the final one is called ferromagnetism, which is an exceptionally strong force of attraction between a magnetic field for iron and a very few other substances, right? Now, most of our discussion will be, and most problems that you're going to face will be dealing with paramagnetism. In other words, basically you need to identify the fact that if you have unpaired electrons in the electron configuration, then that particular atom or molecule, we're dealing with atoms, but it can also occur in molecules. If that's the case, then the particular molecule or atom will display paramagnetism. And I should say ions as well can display that as well, all right? Okay, so how do we measure paramagnetism? Basically, this is a very schematic representation of how we do it. Basically, we have your magnets here, and you can turn on the magnetic field. Your substance will be in this capsule right here, and basically, you're going to record the initial mass of the substance before you turn on the magnetic field, and then when you turn on the magnetic field, the substance is going to weigh more, right? So therefore, even though it seems to suggest that the mass is increasing, it's not that the mass is increasing, it's just that the field that is produced will pull on the substance that is paramagnetic, and therefore a greater mass will be recorded. And therefore, if that happens, that means that the substance must be paramagnetic. All right? Because it is being pulled by the magnetic field. All right? And therefore, it has unpaired electrons as a result. All right? So that's basically what paramagnetism is all about. So usually what questions that you'll be asked dealing with this is that, for example, you're given an electron, you're given an atom or an ion, and you're to find out whether or not it's paramagnetism. If it's paramagnetic, I should say, if that's the case, what you'll find is unpaired electrons in the electron configuration. And I think the next slide is an example of that. Okay, so the next slide says, a sample of chlorine gas is found to be diamagnetic, right? So basically what that means is that it, according to the definition I gave you earlier, the repulsion will take place and not attraction, right? So basically, structures that have that will have paired electrons. Now the question is asking whether or not the gas sample is composed of individual chlorine atoms. And the answer is no. You know why? Because if you look at the electron configuration of chlorine, the atomic number, which is 17, if I were to use boxes to represent it, this is 1s, this is 2s, and then you have your 2p's, 3 of them. 1, 2, 3, 4, 5, 6. So these are your 2p's, and then you have your 3s. 1, 2, and then you have your 3p's, which will have 5 electrons distributed among the 3 p orbitals. And as a result of that, look here, we have an unpaired electron, right? So if it's unpaired, that means that the chlorine atom would be paramagnetic. But the question says that chlorine is found to be diamagnetic. So what does that mean? That means that the chlorine gas does not comprise of chlorine atoms. Instead, it is comprised of, and you all should know this by now, chlorine molecules, which will be Cl2. All right. So the chlorine molecules will be diamagnetic, but the atoms themselves will be paramagnetic. And therefore, since we know that chlorine is diamagnetic, then we know that chlorine does not exist as atoms. It exists as diatomic molecules. All right, so that's basically the answer to that particular question. Okay, what time is it? Okay. All right. Should be able to cover some of these here. Okay, so now we're going to look at the relationship between the positions of the elements in the periodic table and their properties. And in particular, we're going to look at trends in terms of different properties as you go down a group or, well not or, and across a period, right? So that's what we're talking about here. We're talking about what we call periodic properties, right? So there are certain physical properties and chemical properties as well that will recur after so many elements, right? And therefore, that is observed when you arrange the elements in order of their increasing atomic mass. And the scientists or the chemists that first discovered this trend was Mendeleev. I don't know if you remember, we talked about him earlier. He was a Russian chemist, and he basically came up with the first version of the periodic table based on just observing trends as you go from one element to the next in terms of their increasing atomic mass. Back then, nobody knew the exact structure of the atom in terms of the electrons, especially how they're distributed. So therefore, nobody could explain why these trends occur. All they can tell is, okay, as you go from one element to the next, after you reach a certain elements, then the properties tend to recur. All right, so that was basically what Mendeleev discovered. In fact, I don't know if I told you this, when Mendeleev first put forward his idea or his version of the periodic table, there were some gaps in it. All right, there were some gaps in the periodic table which represented elements that were not discovered. And one particular example, a very good example of this would be germanium. Germanium was not discovered until about, I think, 30 years after Mendeleev came up with his periodic table. And based on the periodic table that Mendeleev came up with, he accurately predicted what the properties of germanium would be. All right, and that is without even understanding the atomic structure or how the electrons are arranged. Basically, what Mendeleev did was just follow the trends. And basically, when he predicted the properties of germanium, and when germanium was discovered, there was a very close correlation between what he predicted and what was actually observed when it comes to germanium, right? So when we talk about the properties that we're looking at, we're talking about things like melting point, boiling point, hardness, and so on, right? These are all periodic properties which vary as you go from one atom to the other, either down the group or across a period. So what we're gonna do is look at certain properties which can be explained based on our understanding of electron configuration, all right? Now, the first property that we're gonna look at is the atomic size. And the way we determine the atomic size of a particular structure is dependent on the nature of the particular atom, if it's a metal or non-metal, if it is combined with other atoms to form, what do you call it now, bimolecular molecules, all right? So, in the case of, so the atomic radius can either be covalent or metallic, right? Now, in the case of the covalent radius, like for example, in the case of a diatomic molecule, the radius will be given by the distance between the nucleus and, well, the distance between the two nuclei divided by 2, all right? So if you measure the distance here to this nucleus, where the internuclear distance is 266 picometers, then the covalent radius would be half of that, which would be 133 picometers. And just to remind you, 1 picometer is equal to 10 to the minus 12 meters, all right? Just to give you an idea as to the type of sizes we're talking about, all right? Now, that's for covalent radius. Now, for metallic radius, it's kind of the same thing. It's half the distance between the nuclei of adjacent atoms in the solid metal. So, very similar to what we're talking about here with respect to the covalent radius, all right? Now, what are the trends that we will observe in terms of the atomic radius? Well, basically, let's look at what happens as you go down any group. As you go down any group, it doesn't matter what the group is, what you'll find is that the atomic radius will increase going from top to bottom of any group, all right? And the reason for that is that the radius can be looked at in terms of the difference or the distance between the nucleus and the valence shell, right? And basically the valence shell will be further and further away from the nucleus as you go down the group, right? So the n=1 shell will be closer, then the n=2 shell will be further away from the nucleus, and so on and so forth, right? So that's basically what is observed with respect to the atomic radius, right? So as stated here, as the value of n increases, then the distance between the nucleus and that particular shell would increase, right? So that's basically what you observe when it comes to the atomic radius going down a group. Now, going across a period, what you'll find is that the atomic radius will decrease as you go from left to right within a period. Now, how do we explain that particular trend? All right, so let's think about it. Let's say I take the second period, which starts with lithium, and then it goes across to neon, right? So what are we doing when we are going from lithium to neon? Basically, as you go from one atom to the next, you're adding an electron to the same shell, right? Which would be the second shell, right? So in lithium, you're adding one electron, and then in beryllium, you add another one. So you're gonna have 2 electrons in the same shell, and then so on and so forth until you get to neon. At the same time, you're adding a proton to the nucleus, right? So basically, in the case of lithium, there are 3 protons, and then beryllium will have 4, and so on, right? So 2 things are happening at the same time. You're adding protons to the nucleus, and you're adding electrons to the same shell, which would be the valence shell. So what's the consequence of that? Well, because you're adding protons to the nucleus, you're increasing the nuclear charge. And therefore, as a result, the nucleus becomes more positive and pull the surrounding electrons closer to the nucleus. And therefore, as a result, the atomic size decreases, all right? Now, they make mention here of the effective nuclear charge. What they're talking about is the fact that, again, referring to period 2, in the case of lithium, for example, you have 2 electrons which are closest to the nucleus, and then you have 1 electron which is on the outside in the valence shell, right? So what's going to happen is that there are a couple of forces that are at play here, where you're going to have the attractive forces between the nucleus and the surrounding electrons, but at the same time, the electrons in the valence shell will be repelled by the inner core electrons in the case of lithium, and that trend continues right across the period, right? However, the trend is still that as you go from one element to the next, the size decreases because, again, the nuclear charge increases. That exerts a greater force, attractive force on the surrounding electrons, pulling them closer to the nucleus, and therefore, as a result, the atomic size decreases, all right? So those are the trends that you'd observe. And this chart here is a graph where you're plotting atomic radius versus the atomic number. This is for period 2, this is for period 3, and so on. And in each of these cases, you'll notice that as you go across a period, the atomic size as measured by the radius decreases. That is true for period 2. This is true for period 3. This is generally true for period 4. There's a bit of a kink here. I won't go into the explanation for that. And then in the case of period 5, it's even a bigger kink right here. And in the case of period 6, you have 2 kinks right here in that plot, right? I won't go into the explanation for that, right? But generally speaking, that's what you'll find. As you go down, as you go from left to right of any period, the atomic size decreases, and that's due to the greater attractive force that exists between the nucleus and the surrounding electrons, all right? Okay, so this question says, with reference only to a periodic table, which we have here, arrange the following elements in order of increasing atomic mass. Atomic radius. So remember, going down the group, the atomic radius increases. Going left to right, the atomic radius decreases. You need to remember that, right? So let's look at the first one. Magnesium, sulfur, and silicon. So let's look at their positions in the periodic table, all right? So based on the periodic table that we have here, the first element starting from left in period 3 would be magnesium, and then you have to go across to group 6, where you have sulfur in that same period, and then silicon is before sulfur, right? So remember now, the question says you're going to arrange them in order of increasing atomic radius. In other words, you're going to start from the smallest radius to the largest, right? So between the magnesium, sulfur, and silicon, which one would you expect to have the smallest radius? They're all in the same period. And remember now, going from left to right is how the radius will decrease, right? So between magnesium, sulfur, and silicon, which would have the smallest radius?
Sulfur.
That's correct. So sulfur has the smallest radius, followed by
Silicon.
silicon, and then of course, magnesium would have the largest radius, all right? So that would be the trend with respect to A, all right? Now let's look at B. In the case of B, we have arsenic, nitrogen, and phosphorus, right? So if you look at the periodic table, now remember, going down the group, the atomic radius increases, right? Going down any group, the atomic radius increases. And it just so happens that if you look at the periodic table here, nitrogen, phosphorus, and arsenic are in the same group, right? So let me hear what you have to say about arranging this in order of increasing atomic radius. Which of those 3 would have the smallest?
Nitrogen.
Nitrogen followed by
Phosphorus.
phosphorus, and then followed by, of course, arsenic. And that's it, all right? Okay, so that's the answer for B. So let's look at C. Now, in the case of C, they gave you arsenic, antimony, and selenium, right? Now, let's see where they're located. Okay, so sulfur and selenium is in the same group, but arsenic is just to the left of selenium, all right? So let me hear what you have to say about this one. Which one of these you expect to have the smallest radius between arsenic, antimony, and selenium?
Arsenic first.
You sure about that? Remember, the atomic size decreases as you go from left to right.
So the selenium would be first.
Exactly. Selenium will be first because it's left of arsenic, right? Which one would you expect to be the next in size? Now, in this case, you have arsenic and you have antimony right below arsenic in group 5 of the periodic table.
Arsenic.
Yeah, exactly. Arsenic would be the next in line, followed by antimony. and that's it. All right? Okay, any questions about this? Any questions? Excuse me. All right, so. Moving along, okay, now we're gonna talk about the size of the ions of these atoms, right? And the first thing we're gonna talk about is defining what we mean by the ionic radii, which is what we use to measure the size. And basically, this is the definition right here. The ionic radius of each ion is the portion of the distance between the nuclei occupied by that ion, right? So here is an example. In the case of magnesium oxide, the total internuclear distance is 205 picometers, but it turns out that the radius of the magnesium ion is 65, and the radius of the oxide ion is 140. So that's basically how we determine the radius or the radii of ions, monatomic ions. All right. Okay. So let's talk about what would happen to the radius when something like a metal atom loses electrons. In other words, what would be the size of the ion that is formed from an atom, right? And basically what you see here is what would happen. What you'd find is that cations will be smaller in size compared to the atom from which they're formed, right? And that is true without any exception, right? And we see some examples right here. For example, if you go from sodium atom to sodium ion, look at the difference. Sodium atom has a size of 186 picometers in terms of its radius, but the sodium ion is 99 picometers. So therefore, there's almost a decrease of half or by half when you go from the sodium atom to the sodium ion. The same thing is true and observed when you go from magnesium atom to magnesium ion. In this case, it's more than half in terms of the reduction, because in the case of magnesium, the radius is 160. In the case of the magnesium ion, the radius is 65. So that's more than half in terms of the reduction. And that is true for pretty much any metal ion that is formed from any metal atom. All right. So that's in the case of cations. Now, what about anions? What you'll find is that in the case of anions, the sizes are larger compared to the atoms from which they're formed. All right. Oh, by the way, before I go into that, I should explain why we observe why cations are smaller. The reason why cations are smaller compared to the atoms from which they're formed is that when the valence electrons are lost from an atom, right, from a metallic atom, what will happen is that the nucleus will have the same charge, but the number of electrons are less. And therefore, what's going to happen is that the nucleus will have a greater pull on the remaining electrons. And therefore, as a result of that, the metal cation has a smaller size compared to the metal atom. All right. So that's the reason why cations are smaller compared to the metal atoms from which they're formed. Now, the opposite is true when it comes to anions. What you'll find is that the anions are larger compared to the atoms from which they're formed. Now, the reason why that happens is that, of course, to form an anion from an atom, you add electrons. When you're adding electrons, you're increasing electron-electron repulsion, and therefore what will happen is that the anion will become larger in size compared to the atoms from which they're formed. All right. So that's the reason why anions and hold on, let me see if I have oh, here's an example. So that's the reason why anions are larger in terms of their size compared to the atoms from which they're formed. So if you take chlorine, for example, chlorine has an atomic radius of 99 picometers. When they gain an electron, then the radius increases to almost double the size. All right. Which is 181 picometers. Okay, so that's basically the opposite of what happens in the case of atoms formed or cations formed from atoms. All right. Now, there's a term that I'm going to introduce here, which is called isoelectronic, right? And this is usually in reference to a series of atoms and ions that have the same electron configuration, right? So basically what that means is that they have the same number of electrons, right? And if the sizes are the same, well, the sizes will be different, I should say, if you have different nuclear charges. So let me give an example. Let's say you were to compare the chloride ion to argon, right? Now, in the case of the chloride ion, the number of electrons here would be 18, and the number of electrons here would be 18, right? However, the number of protons in the case of the chloride ion would be 17, and the number of electrons here would be 18, right? And let's say you were asked to determine which one would have the greater size, right? And the answer is the one with the greater size would be the chloride ion. So the chloride ion will be larger compared to the argon. Why? Because argon has more protons in the nucleus, and therefore those protons will pull the electrons closer to the nucleus, and therefore the size of the argon atom would be smaller compared to the size of the chloride ion. All right. So you could be given a question. In fact, I think there's some questions in the assignment which ask you to look at atoms and ions and tell which is larger or smaller in size. So we'll get to that shortly. Okay, any questions about this? Any questions? Any questions? All right, so here is a chart which summarizes what we just discussed, right? So just to explain what we have here. The purple spheres represent atoms. The orange spheres represent ions, cations, and okay, I guess I'm mixing up my colors. The blue spheres represents an ion, all right? So, you know, what I mentioned before can be observed. I can use some examples right here. So for example, remember I said that in terms of the atomic size going from left to right, the atomic size decreases. Well, we can see that here. So if you start with lithium, you see that the atomic size is 152 picometers, and then it goes to beryllium, which is 111, and it continues to decrease until you get to group 7A element, which in this case would be fluorine. And the atomic size for that is 171 picometer, right? And you see that for all the other elements in all the other periods, right? The other trend that we discussed is that as you go down any group, the atomic size increases. And you can see that, for example, in group 1A. In group 1A, you have 152 picometers for lithium, and then it increases to 186 in the case of sodium, and it continues until you get to cesium, which is 265. So that is another observation that we talked about that you can see this chart. And then when it comes to the size of the ions compared to their atoms, if you start off discussing cations, you see that, as we said before, the size of cations will be smaller compared to the size of the atoms from which they're formed. And you can see that in many of these examples here. So for example, the lithium ion has a size of 59 compared to the atom, which is 152. Just to choose another arbitrary example, strontium, the size of the atom is 215, but the size of the ion is 113. Cesium, the size of the ion is 169, but the size of the atom is 265 picometer, all right? And then on the non-metal side, you see that the reverse is true. The size of the anion is greater than the size of the atom. For example, nitride has a radius of 171 picometers, and the nitrogen atom is 75, right? So clearly, the nitride ion is larger compared to the size of the atom from which it is formed. And we explained that, as we said before, when you add electrons to an atom, it swells up because you have more repulsion between electrons taking place, and therefore the size increases, all right? So that's basically what is observed. Let me also point out down here, even when you have the possibility of a metal forming two separate ions of different charges, you see the same trend. If you look at, for example, comparing chromium atoms to the chromium 3+ and chromium 2+, what do we observe? The chromium 3+ is the smallest of these structures, right? Followed by the chromium 2+, followed by the chromium. So what this tells you is that the more electrons that you remove from the atom, the smaller would be the resulting ion, all right? Okay, and that's basically what this chart is all about, all right? So, let's see if you can answer this question. Now, what this question is asking for you to do is not cheat and look at the table that we just looked at. The only thing I'm going to use is a periodic table, right? And the question is asking for us to arrange these structures, species, in order of increasing radius. So you're going to start from the smallest to the largest, right? So what I will do firstly is try to find out which of these are isoelectronic. So what I'm going to do is I'm going to look at the number of protons first in each case. So in the case of calcium, it's 20. In the case of iron, it is 26. In the case of potassium, it's 19. In the case of sulfide, it's 16. And in the case of selenide, it is 34. So that's the first thing I would do, all right? And then I will look at the number of electrons, right? In each case. Now, in the case of calcium, the number of electrons will be 18. In the case of iron 3+, it's going to be 23. In the case of potassium, that will be 18. In the case of sulfide, that will be 18. And in the case of selenide, that will be 36, all right? Now, the isoelectronic species are the ones with the same numbers of electrons, right? So basically, you can order those three in terms of their increasing size. The one with the greater size, or the one that is smallest, let me start off with that. The one that is smallest is the one that would have the greatest nuclear charge, right? Or the greatest number of protons, right? So calcium has 20, potassium has 19, sulfide has 16, right? So I would say that the calcium will be the smallest first, the calcium ion will be the smallest, followed by potassium, which will be next in line, followed by sulfide. All right, so among those three, that would be the order. Now the question now becomes, where does iron 3+ and selenide comes in? Okay, the selenide is easy to tell because selenide would be below sulfide in the periodic table. Going down any group, the atomic size, or in this case, the ionic size would increase. So I'm going to put selenide right here, right? So the next question is, okay, where does Fe3+ comes in? Well, Fe3+ is in the same period as calcium, right? So going across that particular period, Fe would be smaller in size compared to calcium because Fe is to the right of calcium. So I'm going to put Fe right here, Fe3+ right here. And that's it. That's basically the sequence in terms of increasing radius of these species. All right? Okay, any questions about this? Any questions? Any questions out there in Zoom? Any questions? All right. So let's go back to the assignment. And in part C, they're basically asking the same thing as we just did. All right. Okay, so let's look at A. Again, you have to order them in terms of increasing size. So of these three, Fe2+, Fe or Fe3+, which would be the smallest? Which one would you expect to be the smallest?
Fe3+.
Fe3+ is indeed correct, followed by Fe2+, and then Fe. Very good. And the reason why Fe3+ have less electrons compared to the others, so therefore the nuclear charge pulling them together would be greater, and therefore that would be smaller. And then Fe2+ would be the next in line, followed by Fe. All right. Okay, very good. Let's look at the second series. You have sulfide, argon, and selenide. All right. Now, as I said before, when it comes to these structures, I like to look at the number of protons and electrons, right? So in terms of the protons, sulfide will contain 16, argon will contain 18, and the selenide will contain 34, right? And then in terms of the electrons, the sulfide will contain 18, argon will contain 18, selenide will contain 36, right? Okay, so these two are isoelectronic because they have the same number of electrons, right? So between those two, which one do you expect to be the smaller of those two?
Sulfide. I mean
So
argon. Yeah, argon.
argon, because argon has a larger number of protons, so therefore it will have a greater pull on the electrons surrounding it. So therefore argon will be first, followed by sulfide. All right, and then the selenide, that's easy because selenium is right below sulfur in that group, so therefore you'd expect the selenide to be larger in size compared to sulfide. So therefore, this will be the answer for D. All right. Okay, any questions over that one? Any questions? Any questions? Okay, let's look at. I'm sorry, let me clear this first. Let's go down. Okay, let's look at C. Now, in the case of C, we have aluminum, chloride, sulfide, and potassium. So again, what I like to do is, I like to write down the number of protons and electrons. Aluminum is 13 protons and 13 electrons, right? Chloride is 17 protons and 18 electrons. Sulfide has 16 protons and 18 electrons. And potassium has 19 protons and 18 electrons, right? So these three are isoelectronic because they have the same number of electrons, right? So based on the number of protons, which would be the smallest of those three? They have the same number of electrons. And remember, we said that the greater the number of protons, the greater will be the pull. If the number of electrons are the same, the greater will be the pull of the protons on the electrons, and therefore that will make it smaller. So which of these three would you expect to be the smallest in terms of size?
Chlorine.
You sure about that?
Would it be potassium?
It will be potassium, yes. Because potassium has a higher nuclear charge compared to chlorine. What's the next in line? In terms of size, which one will be larger than potassium in line? Well, I'm sorry,
Then would be.
will be chloride, exactly. And then the next one will be what? What's the next one?
Sulfur.
Well, sulfide to be more.
Sulfide.
Okay, so this begs the question, where does aluminum fall within this series? Well, aluminum, let's see where aluminum is. Aluminum is above. Okay, so let me just say this. The potassium. What should I put this? Let me see here. So it's potassium, chloride, and sulfide. Sulfide and chloride are in the same period. But aluminum is in the same period as sulfur and chlorine. But aluminum is to the left, right, of sulfur and chlorine. So aluminum would be small in size compared to sulfur and chlorine. But the question is, aluminum is kind of weird because it's not isoelectronic. It's 13. It is in period 3. So aluminum, if it was atoms themselves, the aluminum would be smaller than phosphorus and sulfur. Oh, and chloride. So I will put aluminum here. I'm going to recheck this to make sure, but I think aluminum should go here. And the only reason I said that because the chloride and sulfide would be larger in size compared to the atoms from which they're formed. And I suspect that to be, I suspect the potassium will be greater than aluminum as well. So I'm going to check on this, but I'm quite sure aluminum is the smallest of those four. All right. D. Sulfide, chloride, potassium, and calcium. Okay, so again, I'm going to write down the number of protons. Protons in the case of sulfur, that's 16. In the case of chloride, that's 17. In the case of potassium, that's 19. In the case of calcium, that's 20. And in terms of the number of electrons, sulfide would have 18. Chloride would have 18. They would all have 18. So this one is easier to do. Right? So which would you expect to have the smallest radius? They're all isoelectronic. They all have the same number of electrons, but the number of protons are different. And remember, in an isoelectronic series, the greater the number of protons, the smaller would be the size of the atom, right? So based on that, which one would you expect to be the smallest?
Calcium,
Okay, then,
potassium,
and then,
chloride,
and then,
sulfide.
that's it. All right? So that's basically how that is done. All right, any question about it? Any questions? Okay, is there any more to this one? Oh, no, that's it. All right. So I think I'm going to stop here because the next topic is a bit involved. That's called the ionization energy trends. All right, so that's the next topic we're going to discuss. And that's it for today. So just to remind you, Tuesday, no classes, all right? So I won't see you until next week this time. All right, so that's pretty much it. So enjoy your weekend. I see you next Thursday.
Have a great weekend, Professor.
Yeah, you too. Okay, for those of you